Hello, I'd like to go over some of the key elements of Unit 4 Module 1. Several questions that were asked during office hours by different students, but the same questions, so I thought I would put together a video where some of the common questions are answered and that you can see some of the fundamental problems worked through and compared to your notes. So the first question, this was on the Friday study session, and what we're asking is, does this reaction have a limiting reactant? And if it does, what is it? So the first thing we do is account for all the particles. And two, we subtract off the excess. So excess is going to be reactant that wasn't fully reacted, and so that wasn't completely consumed in the reaction. And that happens to be nitrogen. So we remove the nitrogen and we get 2N2 plus 6H2 to make 4NH3. The final step is to divide by a common multiple. And so we show that here. So we account for all the particles, we subtract the excess from both sides, and then we divide by the multiple. And that gives us our balanced reaction. And now we say, well, was there a species that was present as a reactant but was fully consumed? And if we had more of it, we would make more product, right? Because that's the real definition of a limiting reactant, is what species, if we had more of it, would we make more product? It's not going to be N2 because we know we have more N2 at the end of the product, at the end of the reaction. So in that case, it would be hydrogen. And so we would pick the answer B. B is hydrogen is what's limiting the reaction. If we had more of it, we expect to make more product. Question 2 is about the balanced reaction, which we just did in the last slide. So we account for all the particles, and by doing that, subtracting off the excess, we see we have N2 plus 3H2 to make 2NH3. And what we're going to do now is just double check all that. So if we counted up all the particles, the nitrogen particles in the reactants, we'd have 2. In the products, we have 2. Check. We have 6 hydrogens in the reactants, 6 hydrogens in the product. So we would consider this to be a valid balanced reaction. Question 3 asks, which diagram best describes the release of 210 kilojoules per mole? And when we say release, that means that the reactants have higher potential energy than the products. And the process of going from reactants to products release energy like a waterfall. If we use the gravity example, so energy is released to the surroundings as R goes to P. Right, less stable reactants, more stable products. So release energy is considered exothermic, and that would be A. B and D show the same potential energy, so there's no energy release. And then C is showing classic endothermic behavior. So our selection here would be A. This is the first question that we had today in today's activity. And so there's multiple right answers, so let's take a look at this. The reactants are higher potential energy than the products. So this is showing classic exothermic behavior. So it's not endothermic, it's exothermic. There's a positive activation energy for the forward, and there's all activation energies are always positive, right? It happens to be smaller for the forward reaction than it is in the reverse. But they're both greater than 0. They're always greater than 0. And we see that the reverse activation energy is greater than the forward reaction. This is characteristic of an exothermic reaction when the products are more stable. And so we would pick B, C, and E. This is an analysis, a quantitative analysis of the activation energies. And in this case, I put some numbers in here to help us keep track. We'll need that in the next slide. So the forward reaction is endothermic, meaning the products have higher potential energy than the reactants. and it's endothermic by about 50 kilojoules per mole. And in the reverse, we're starting with products and we're making reactants, and in that case, we have an exothermic reaction. And this demonstrates that if we have an endothermic reaction in one direction, we must have an exothermic reaction in the opposite direction. That answer is B. So B, the reverse direction, is exothermic, meaning going from right to left is releasing energy, but going from left to right, or reactants to products, it is endothermic. They're definitely not the same energy, and it's not forward exothermic. Now we're going to quantify it. So we put the numbers back up there. And so from the reactants forward direction, right, we're going from 25 up to 150. So that's going to be positive 125. And in the reverse direction, we're starting at the products at 75. We have to go up to the same 150. So that's going to be plus 75. So the forward activation energy is 125. The reverse activation energy is plus 75. So remember, they're always positive numbers, and that's how we would calculate them. And remember, they're going up to the top, the activation energy or the transition state. So we're now looking at a chemical reaction panel, and so we account for all the particles. So 4 oxygens plus 4 SO2s make 4 SO3s plus 2 O2s, right? So this is just accounting for all the particles we see. That's step 1. Step 2 is to remove the excess oxygen, because it's present on both sides. And that gives us 2 oxygens plus 4 SO2 plus 4 SO3. That also means that we know SO2 is limiting if O2 is in excess. And then is there a number we can divide all the coefficients by? The answer is yes, 2. And so our final answer should be 2 answers. D, that we have 2 SO2 plus O2. And again, these are the steps. Account for all the particles, subtract the excess oxygen, and divide by a multiple to reduce coefficients. And then the second answer is B, right, that SO2 is a limiting reactant. In this case, we had lots of questions regarding configuration effectiveness. Hopefully it makes more sense now after today's lecture. And so we look at reaction A. We have 2 A's making reacting with 1 B, so 3 particles colliding in the forward direction. In the reverse direction, we have only 2 C's colliding. We would expect the 2 C's that collide to find each other to be statistically more probable in the reverse direction. So we expect the forward to be slower, the reverse to be faster, and so the net result is going to be a buildup of reactants, because reactants are very, very slow to react. When they do, they make a product that reacts very quickly, much quicker than the production of it, and eventually makes a buildup of reactants. While B has the opposite case. We have 3 particles needing to collide in the reactants to form products. But in the products, we have 4 particles required. So this is going to be much less likely. The 4 particles collision is going to be much slower. And in that case, if the 4 particles, which are the products, are slower to react, then that would result in a net buildup of products. And so we would expect this to be product favored, given that the reverse direction happens so much slower. So that means B would definitely be the case where we would have product favored, more products than because the reverse direction happens so much slower. C would have the same rates because you have 3 particles on one side, 3 particles on the other, so that would be the same, and A would be wrong. So B is the right answer. Since 3 particle collisions would be more likely than 4 particle collisions, we would definitely expect the answer to be B. And so for the final slides that we talked about with equilibrium, We just have to keep in mind that at equilibrium, reactants and product concentrations, they do not change with time. There's always some amount of reactant left over as products recombine to form reactants. So equilibrium is this nice boring time when reactants and product concentrations do not change, while contrary to popular belief, it's not when the concentrations are equal, right? That's not what equilibrium is. Equilibrium is when reactants and product concentrations do not change. All right, so good luck, everyone. This covers most of the most commonly asked questions regarding the homework for Unit 4, Module 1, and the quiz taken on Friday.